In addition to evaluating composite functions, as we did in the previous video, we can also find a new composite function by plugging one entire function into another. We've done something like this before, however we're going to use a new notation this time. The little circle just means the function f is going to be composed with the function g, and specifically what that means is I'm going to take the g function and plug that in to the x in the f function. So for example, I'm going to start by writing down the f function, which is 2 times x, but I'm not going to put x down, I'm going to put a blank space, squared, and then minus 3. And then since I'm just plugging the g function over here into the x spot right there, in that blank space, I'm just going to write the g function, which is 4x. Okay, and from there I just do some simplifying. So let's do exponents first. 4x times 4x is 16x squared. So this becomes 2 times 16x squared. And then minus 3. From here I can just multiply these numbers together. 2 times 16 gets me 32. So 32x squared minus 3 is as simplified as I can get. And there is my brand new composite function. Notice it's not a single number I got, it's a brand new function. As we talked about in the evaluating compositions video, if you watch that one, the order matters. So this time I'm going to do g composed with f, the opposite composition of what I just did. In other words, the f function is this time going to get plugged into the g function. So this is going to get replaced with this x over here. And as we saw, the order mattered last time. Let's see if the order still matters. So I'm going to do 4 times x, which is that g function. But in place of x, let's write the f function, what we're subbing into this one. So 2x squared minus 3. I'll go ahead and distribute. So I end up with 8x squared minus 12, and that's as simplified as it can get. And I can see that, yes, once again, the order does matter. I have a brand new, completely different composite function when I do this in a different order. Okay, and then finally, we can also take a function and plug it back into itself. So I'm going to plug the g function into the g function. Well, the g function is 4 times x, but in place of x, I'm going to put the g function, which is 4x. So simplifying this, I get a new function when g is composed with g, of a new function that's just 16x. One thing we haven't done so much with yet is finding the domain of a composite function. To do this, there's really 2 steps of it. You need to consider 2 different domains. First of all, you need to consider the domain of, I'm going to call it the second, I put it in quotes, the second function, meaning this part right here, the second function in our composition direction. So in this case, the g function, there really isn't any domain restriction. My function is just 4 times x. X can be whatever I want it to be. So I'm going to say my domain is all reals, or just negative infinity to positive infinity. However, we don't just have to check that, we also have to check the domain of our final answer, or our composite function. Well, this is just the same example from the last slide, so I just rewrote the function down here when we did f composed with g. And this time, when I check for x, once again, there's really no domain restriction because x is just getting squared. So once again, my domain is all reals, or negative infinity to positive infinity. Things that you wouldn't have a domain that's all reals would be if you're taking a square root, you wouldn't want to take the square root of a negative. If you had a fraction, you wouldn't want to have 0 in the bottom of a fraction, and similar things. In our next video, we'll take a look at somewhere our domain does have a restriction. So then what I need to do, getting off track there a little bit, is to state my final domain then of this entire composite function. The 2 things I need to check are, well, the second function, which we said the domain was all reals, and our composite function, which we also said the domain was all reals. And so putting those pieces together gets me a final domain of, well, you guessed it, all reals. X can be whatever we want it to be. There's no problem with this. In our next video, we'll take a look at what happens when we don't have a domain that's all reals.